I'm as organized as I'm going to get. It's a snow day in Rome and Floyd County, and so my toddler is with the babysitter for like the next hour and a half. And so I got here like 10 minutes ago. And so I didn't have my normal time to look over my notes or, make sure I have everything. It is a snow day officially because they were concerned about it icing, blah, blah, blah. Anyway, Sabrina. Yeah, so Rome City schools were already off, and then Floyd County was not going to be off, and now it is off, and if county schools are off, and the daycare is closed. So, I'm a little less put together than normal, if that's possible. But, I did remember to bring the quiz. I forgot most of my PowerPoints, but I remembered the quiz. So you have an individual quiz today. Let's see, we have Mastering due tonight, which covers stuff that we did last week. And there's Mastering Wednesday, which covers some stuff. We're going to finish Chapter 14 today. So by the end of the day, you can definitely do the homework tonight and Wednesday night. And then we'll do a group quiz on Friday, getting ready for Chapter 15 and stuff. Alright, I want to do 2 more practice problems where we manipulate K, move around our equations to get K in the right orientation, and then talk about Le Chatelier's principle, and move on to Chapter 15. Go team. Alright. Alright, so let's say, for example, I have this original equation. I have nitrogen and 3 hydrogens combined together to make 2 ammonia with a K of 3.7 times 10 to the 8. So I have the original equation with the original K. I have now done some things to this equation, so now I want to find the new K for this equation. So, what have I done to the original equation? 2 things. I flipped it over, and you can call it a few different things. Either multiplied by 1/2 or I divide everything by 2. Both correct. Alright, so since I reversed the direction of it, what do I do to my original K? Okay, flip 1 over. And then because I divided the whole thing by 1/2, what do I then do to it? Raise it to the 1/2. Then what is that? 1 over 3.7, 8. Raise to the power 5. Have those playing along at home. You guys get the same answers I did. 2 people are nodding. I'll take that as consensus. Good. Oh, sorry. I was just saying that you want to get something other than that. Did I do it right? Mostly just talking to myself anyway. Half the time it's just me talking out loud to myself. Let me ask this question. Which direction is K1 telling you about the direction of the reaction? Is it mostly going to make products or mostly make reactants with this value of K? Mostly going to make products, right? The K much greater than 1. So if I flip it over, what would you expect the K to then be in the direction of? Does this K tell you that? Good. So when you do these, that should be one of the double checks in your toolbox to check and make sure you get the right answer. If you know in the beginning, oh, this is definitely going to make product, and I reversed the reaction, I should definitely have a K less than 1 to tell me which direction the things are going. Okay, let's do my trickier one. Yeah. Oh, right, because this was 2 and now it's 1. And so I divide the whole reaction by half. Or multiply by half. I guess half works either way. Alright, let's do a trickier one. And these are as tricky as I can possibly make them. So if you're feeling confident, that's it. I can't do anything else other than these 2 or 3 things. Let's say I have Alright, so that's the equation I want. I want carbon dioxide reacting with hydrogen gas to make methanol and water. I want to know what the net K of the whole of this reaction is given the following 2 reactions. So that's equation 1, and then equation 2 is Alright, so we have these 2 equations, and we have to figure out how to recombine them to get the K net. Wait for everybody to catch up. Alright, so looking at equation 1, are the products and the reactants on the correct side? No. What do I need to do to equation 1 to make it work? Right, and then flip it over, because I want water as a product, and I want carbon dioxide as a reactant. So I have to flip equation 1 over. If I reverse the direction of equation 1, what do I do to its K? 1 over it, okay? Which is, I think, okay. What do we need to do about equation 2? Divide by 2, or multiply by 1/2. Both would be fine. That's going in the correct direction, right? I don't need to do anything else. Just change the coefficient. Okay. 2.8. Yes. Yes. Yep. However you change the coefficient, so it's typically either you divide by 2 or you multiply by 1/2. So either way, it's half as many as it was. Yeah. A second. Let's see. Oh, here we go. 2.8. No. 3. Yeah, I get 5,000. 1, 2, 3. Alright, so I want to do 2.8, 7, 3, 2.5. Oh, we're not there yet. Yeah, that's like step 3. That's just getting the 2 new values of k. So then k net is those 2 multiplied by each other. So that 1.0, -6, 5.3, 2, 3. I think that's one of the ones off your mastering. If it's not, it's pretty close. That's as tricky as they come. So either you're looking for k net, like it is in this one where you combine 2 equations, or it's just this where you just compare the original to the new and you figure out how to manipulate the k. That's the only 2 ways these problems work out. Oh yeah, sorry. Alright, so now that we know lots of things about k and lots of things at q, Le Chatelier's principle is the thing that kind of pulls those 2 things together and helps us figure out if we are at q or k, how do we get to k, because everybody always wants to be at k, because it's the cool letter of the alphabet. So, under my pile of paper something. Oh, okay. So, Le Chatelier's principle is defined as any change in any of the factors that determine the equilibrium conditions of a system. If you make a change, right, then the system will have to change to compensate for it. Is the general idea of Le Chatelier's. And so systems always want to be at equilibrium, and they will do whatever they have to get back to equilibrium. So let's say we have which example is this one? Oh, I'm not ready for that one yet. Let's say we have this. And just as a reminder, let me put this over here in the other box. Right, those are our three positions that Q can be in. It can either be less than K, greater than K, equal to K. Where are we at if Q equals K? Right, we are at equilibrium. If we are at Q less than K, what does the reaction have to do to get to equilibrium? Yep. Then this must be shift left. Alright, so let's say I have this reaction and it's sitting happy, it's at equilibrium, and I do something to the reaction. Let's say what happens if I forcibly add more nitrogen dioxide to the reaction? What will the reaction choose to do to get back to equilibrium? Shift left, right? Because I just put in a bunch more products. So it's going to have to shift left to balance everybody back out. Okay? What Q value would this be then compared to K? Right? Q is now greater than K. So even though we don't know what K is or what Q is, we know that there's too many products. We must be at a point where Q is greater than K. We'll have to shift left, balance things back out. Okay? What if I'm going to make more space for myself, sorry. It's a long train of thought. And I'll pick a slightly different example, a more obvious one. Alright, so here I have the same one I had before, right? Nitrogen, hydrogen, making ammonia. Alright, so what's going to happen to this reaction if I decrease the volume of the container? What is the equation that we have that talks about volume and gases? Last semester. 3 words. Something, something law. The ideal gas law, right? P equals nRT. Alright, so the question is, if I have decreased the volume, what have I done to the pressure? Right, they're on the same side. So if I decrease this, the pressure must have increased. Which makes sense, right? I have the same kinds of numbers of things going on inside the flask. I just squish them closer together, so now the pressure's increased. Alright, so if I've decreased the volume, I've increased the pressure. Has R changed by doing this? Have I told you anything about the temperature? So what's the only other variable I can now do something about? Moles. I can choose the side of the reaction that has the least number of moles to compensate for this. Right, so now I have increased pressure. I want to get back down to regular pressure. To change the pressure, I can change the number of moles. Right, so R is constant, T is constant, we can change the number of moles. And I want to change the number of moles so that the pressure goes down again. So do I want more moles or less moles to have less pressure? Less, right? Less moles, less pressure, because they're on the opposite side of the equal sign. Less moles, less pressure. How many moles are as reactants? How many moles are as products? Which side should I be on then? I want to be on the product side, right? There's less moles. That's going to be a caveat, right? So when you go back and look at your notes, remember, this is just in this case because I have 2 mole products. Now I have 4 moles reactant. So it's going to depend on which one you have more of. So which direction, left or right, does this reaction need to shift to get back to perfect equilibrium? Yes. Yes, that's what you saw in lab last week. Hopefully. Apparently not every lab saw something amazing. But in general, if you change the pressure, right, it got darker, it got past equilibrium, then as you left it, it re-equilibrated. It would go back down towards the side with less moles, which was the colorless side. It can change back. Once you change the pressure, it will find a way to go back. Even if that means going back to reactants, it will choose that to compensate for the pressure change. Yep. All right, I have a third scenario that we're going to look at using all this. So we'll do the first 2 again, and then we'll look at something else. All right, so here's my example. I have 2 sulfur dioxides and an oxygen gas making 2 sulfur trioxides, I guess. Why not? So let's talk about what happens when I do each of these 3 things, and then we'll do a 4th one. I think you guys are ready for it. All right, so if I add more sulfur dioxide, am I adding more product or more reactant? I'm adding reactant, SO2. So what will the reaction want to do to compensate for me adding more reactant? Yeah, it's going to shift to the right. What if I take away some reactant? I take away some of the oxygen. It's going to want to shift left. Like the first 2 seem common sense, right? Just trying to get back to where you are. Let's talk about decreasing the volume. If I have decreased the volume, I've done what to the pressure? Okay. So what do I need to do to the moles? I need to decrease the moles, right? So which way should I go? Right, this side has 3. This side has 2. Right, so I'm going to go to the right in this case. Funny, I can see all your hand directions. From up here, you're backwards to me. So I'm looking at you going, wait a minute. And then I remember, oh, if you turn around, you'd be going the right direction. Sorry. So, yes, shift right. All right, so ready for the tricky one? What does this equation have that all the other ones didn't have? This delta H factor, right? All right, so let's say in my fourth case, I choose to heat the reaction. Yeah, just a minus sign. Yes. So I now have an exothermic reaction. So as an exothermic reaction, did I put heat in as a reactant, or do I get it out as a product? Out as a product, right? It's releasing heat to the surroundings. So you can almost think about it in terms of the other product is heat. Also, if you write that down, it makes it more obvious which way we're going to go. All right, so now if I heat the reaction, so I add heat as a reactant, well, add heat to the whole thing, I guess, to the whole equation. Which way will the reaction want to go to compensate for all that extra heat? To the left. To the whole thing. You can think about it as adding heat right here, right? If heat's in the equation, if I add more heat, right, now we're back at disjointed equilibrium, and so now we have to go this way. Yes. So for example, can I flip this over so everybody have this? I'll do another one. What if I had yep. What if I had, let me make up an equation. We'll do this one. N. Sorry, it's an N. My N's a little crazy. Alright, so let's say I now have an endothermic reaction, right? If it's an endothermic reaction, is heat a product or a reactant? It's now a reactant, right? So you can think about it as this. So what if I add even more heat to this reaction? It's going to shift to the product, right? It's going to shift right. You are adding heat to the whole thing, but only half the reaction wants the heat. Does that make sense? Only the reactants or the products can use the heat, and so only that side that can use it is being affected by it. Good there? Yeah. Sure. Difference between double and quadruple. Let me think what the question is. It shouldn't matter unless they're asking for a quantitative answer. No. No. Unless you're comparing them or trying to calculate an answer. It shouldn't make any difference. Other questions about Le Chatelier's and which way someone goes when they're forced to do something? Okay, in that case, let's talk about Chapter 15. And if you have your notes, great. I forgot to bring my PowerPoint, so my PowerPoint all looks like blank pieces of paper. Imagine this says Chapter 15. I printed them off. They're sitting on the printer. Alright, so Chapter 15 is all about acids and bases. I'm only going to talk for like 2 or 3 more minutes. Alright, acids and bases are an applied way to use all those big K's. That's when spontaneous cheering comes out. Yay! I'm so excited. I get to apply all the knowledge I just have. Yay! Alright, so alright, there's a few, well not a few, there's two main ways to define what an acid and a base is. First one's called the Arrhenius acid-base definition. This is probably the one you use most often. So if I said it was an acid, you would say it releases what? Like H pluses, right? Or protons. Right, something that gives away protons. If I talked about base, it would release what? Hydroxides, yeah. If we use that definition, we can talk about, right, hydrochloric acid. Is an acid because it releases protons. This is only a one-direction arrow, so what does that tell you about its equilibrium constant? It is so gigantic, it's impossible to calculate, right? Because K is a measure of making products over making reactants, and if there's zero chance of making reactants, what would the denominator be then? Right, because it's product over reactants. If there's zero chance of making that, what's a fraction divided by 0? The black hole. Your calculator freaks out. Nobody can handle it. It's considered infinite, gigantic. So it has a one-direction arrow because it cannot go back to products. That'll be important later. We'll bring it up again. Right, and then that would be a base, right? Something it's releasing hydroxides in solution. Those are great, but those are like high school definitions. We don't use those. You guys are ready for the real definitions. We're going to use the Bronsted-Lowry definition, which his name is German, so it has that weird slash through the O, which I don't speak German, but apparently that means something important in their language, so I'm probably misspeaking his name. But, Bronsted-Lowry definition. An acid is something that's going to donate a proton. It doesn't release it to the water. It specifically has a target for that H+. The H+ is specifically going to another compound. and it's specifically going to a base. And this way, they're linked. You have to have an acid-base pair. The acid gives away a proton to a base. That's who gets it. Let me do my one. Which one should I do? Let's do that. Alright, so I have ammonia and water. Alright, this happens to be an equilibrium reaction. So one of these compounds is going to donate a proton, the other one's going to accept the proton. So, using this definition, which of my two reactants donated a proton? The water or the ammonia? Water was the acid, and ammonia was the base, because it accepted it. Because it's in equilibrium, it can go in reverse. If I look at this reaction in reverse, is NH4 going to give away its proton or take another one? Give it away. So if it gives it away, what is it? On both sides of the arrow, you have an acid base, and what was the base turns into the acid, and what was the acid becomes the base. We'll do so much more with this for the next 3 weeks. Alright, you will need a calculator for your